Hmm? Say hello. Say hello.
How are we?
Say hi.
Is that a kid Kenya?
No. Oh, what?
My, she's young, huh? She's only
She's
like 1.5,
2.
maybe 2.
Yeah, she's gonna be 2 in November. Okay, you gotta go now. Bye bye.
Bye bye.
No, don't.
Come on, go to Dada.
Okay, bye. She doesn't want to go. She's like laying in my room.
Yeah.
Bye. Oh, you want to come class?
Okay.
She said she wants to come to class. Come on, vente pues. Ven para acá. Pero tienes que poner atención, ¿ok?
Oh, poner atención. Oh my gosh. All this pressure. She's so young.
I know.
She's so young and all this pressure.
She's sending kisses.
Alrighty.
Mira.
Hi, Kai. Hi, Adam. Mhm.
Hmm? ¿Te gusta?
Sheep. Yeah.
I'm looking at my drink, bro.
Oh, I'm going to share my screen, right? Can you guys see the PowerPoint, right?
Yes.
Okay. Excellent. Thank you.
She went back to her mom now, so everything.
Oh my gosh. Oh my gosh. It's all right. Oh gosh. I've literally got 3 microphones. Kind of weird stuff. But, okay. So I have a little PowerPoint for us to go through today. And oops. Yeah, so it won't be, shouldn't be too long. But I'm going to wind up fluorescence a little bit, then we'll introduce some concepts regarding quantum dots or single molecule fluorescence and then quantum dots. And I'm hoping to hear more about these latex nanoparticles with quantum dots in them, but I'm not sure. So let's see. Translation. But so hello, Richard. Hey, Kun, how are you?
I'm good. How are you?
Yeah, excellent. I'm gonna mute. Oops. I was trying to mute Richard and I muted Aditya. Hey, Ivy. So, so last time we went on and on about how the lifetime of a fluorescent molecule determines how bright it can be under luminescence, right? Like, I mean, obviously there's other factors, like the quantum yield will determine the proportionality between or part of the proportionality between the radiation intensity and the fluorescence intensity. But then the other part of that is the lifetime, the excited state. So short lifetimes mean brighter fluorophores. And then higher quantum efficiency, i.e. less quenching, less non-radiative relaxation, that means a brighter fluorophore. So those aren't really so deep, but I just wanted to review them quickly. And you guys can see here, for example, is a very, one of the very earliest uses of fluorophores in science, and that's for staining cells. And the interesting thing here is that they have 3 different types of fluorescent dyes, Nappy, Fitzy, and Tritzy. I don't really know what they are, but the dye molecules associate with different structures in the molecule. So the blue are from the Dappy diacetyls, and they tend to stain nuclei, right? Then microtubules, which are these filamentary, thought to be support structures within the cell, they pick up the green dye. And then actin, which is a part of the muscle, actin and myosin are 2 parts of the muscle actuation within muscle cells. They are stained red, right? And so this is a fantastic and fantastically high resolution image. And I do not know if this image was taken using a super resolution fluorescence microscopy or whether it's normal optical resolution. It seems to me like it could be super resolution. Now, okay, we could talk about super resolution another time, but interesting subject. It was the Nobel Prize in, I think, chemistry a couple of years ago. But gosh, I'd love to talk about it right now, but let's put that off. So, a photon encounters a fluorescent molecule. The molecule absorbs the light, creates an excited state, which then relaxes and emits a new photon at a new frequency. So the new frequency is higher or lower than the incident frequency? Who knows the answer to that one? So I give you a clue, E equals H nu, right? So if the photon coming out has to have, can the photon coming out have more or less energy than the photon going in under normal conditions? Okay, less energy, lower frequency is correct. That was contribution from Adam. Thank you, Adam. And you can see it clearly here because, sorry, on this Jablonski diagram here, the incident radiation raises the energy level from the ground state of the ground vibrational state of the ground electronic state up to some excited level vibration within the excited vibration electronic state as sworn. Then there's vibrational relaxation and then emission into a variety of vibrational states in the ground electronic state. So essentially the excitation and the emission differ by, or the absorption and the emission, better said, differ by about twice the vibrational energy loss of the molecule. Does that make sense? So the total Stokes shift. I want to write insert text box. Yeah. So this is basically the Stokes shift here. So Stokes shift is what's normally seen in condensed phase type spectroscopy. Go down to 0 degrees, put it in a solid, go down to 0 Kelvin, close to 0 Kelvin in the solid. Then a lot more happens at resonance wavelengths. So you can do a lot more with putting photons in and seeing the same photon energies. So if you take a molecule like anthracene, which is, I think anthracene is 3 benzene. Let's look at it. Yeah, anthracene is just this stupid guy right here, right? And the excitation spectrum looks like this dashed line, right? So you can see that there's a couple different electronic states. I think we're probably sampling one centered on 250. Then these could be electronic or vibrational or some combination of electronic and vibrational states out here. But it's interesting. Well, I don't know if this thing is emissive or not, but you can certainly pump energy into this 250 nanometer state and recover that energy from this manifold here that shows up around between 300 and 400 nanometers in excitation, or 350 and 500 nanometers in emission. So to properly characterize anthracene, you would have at least 3 electronic states, right? 1 ground, an S1, and an S2. And so in order to see this peak, this excitation peak, we would set the emission right around here, around, say, 425 nanometers, right? or 397 in this case, around 400 nanometers, right? And then you would simply scan the excitation monochromator over these peaks. And so that's basically that now. So this doesn't necessarily involve anything regarding spin triplets, right? The spin triplet is a phosphorescent state, which forms generally from an excited singlet when there's a change in spin state of one of the electrons. And that, and I presume that's the excited electron. But that spin triplet state there then can relax down, but it generally does so much more slowly than the fluorescent processes here. So let's just look at those processes and we can draw some actually, why don't I don't have my pen. Okay. So this is so there's which one of these many arrows here corresponds, would you say corresponds most closely to the excitation of this peak here? Corresponds to the absorption of light indicated by this 250 nanometer peak here. And let's just pretend that this does have a triplet. It's got a singlet and a triplet state, and this is mostly phosphorescence.
Is it the first long arrow from left to right?
Exactly right. It's this arrow right here. And if that didn't immediately come to mind for you, I want you to ask Adam how he made that choice.
Hopefully everyone, it immediately came to mind.
Yeah. Kai, did you know the answer to like which upward going arrow this peak corresponded to right away? No, you didn't. Okay. So Adam explained to Kai how you identified this peak with this arrow.
I did it graphically, so that peak has the most amount of energy being absorbed. Therefore, it should correspond to the highest energy state, and that would correspond to that arrow.
Okay. So when you say it has the most energy being absorbed, what are you referring to there?
The highest intensity that is seen.
That's a mistake, actually.
You mean like, is it the one that's excited, so it's going to be all the way to the top?
Or I should, maybe the wavelength. So it's at the shortest wavelength,
Right.
the highest energy.
Yeah. This shortest wavelength corresponds to the longest arrow, right? So everything in the excitation scan, which is this dashed line, right, corresponds to an absorption or an upwardly going arrow, right? So essentially, everything we can see on this spectrum here should be upwardly going arrows in this Jablonski diagram. Now, because Now, this manifold here is not indicated in this Jablonski diagram. They would be upwardly going arrows from this state up into these states, right? And these would be these upwardly going arrows here. They'll be very weak. They'll be sort of near baseline if this is actually a triplet state. Or they'll be stronger if this is another singlet state, right? We have to, in our mind, we have to possibly change this T designation here to S in order to analyze the spectrum. So an arrow on the left here, that's this long, will correspond to chi, a long or a short wavelength. A long arrow will correspond to a wavelength around 450 or a wavelength around 250. So what's Kai's chance of getting this correct? About 20%? Because it's A or B, right?
What was A?
Okay, so around 250 nanometers, that corresponds to an upward arrow that's long like this, or another one that's short, like sort of the reverse of this one. This one they're going.
The short one?
250 nanometers is the short one or the long one. And that is wrong. So you went with the 4/5 choice. 250 nanometers is blue. So it is the longer arrow, right? All right. There you go. It's always true. So, so now, in this Jablonski diagram, where might these this solid curve here corresponds to downward going arrows. This is an emission scan.
Like the shortest one, like the shortest dot here.
So so the shortest would be these guys, right?
Oh no, not that one. It's like there's like the Roman numeral number 2. Is that the one? Like,
Roman number 2.
Yeah.
These guys up here.
Yeah. Yeah.
Okay. So that's good. I'm glad you said that. Because dashed arrows they correspond to non-radiative decay.
Oh, okay.
So it can't be the dashed arrows. This manifold here has to correspond to radiative decay, which is a solid arrow. Right? There's in this diagram, there's absorption and emission, and then there's non-radiative decay, all kinds of non-radiative decay here indicated, including this weird one here. And there's also intersystem crossing here, process V and IX 5 and 9, right? So the only luminescent ones are this absorption, these two emissions. So now there's two possibilities for this this emissive transition here in the emission spectrum. Starts at 350, goes to about 500 nanometers. And what are the possibilities for correlating this to arrows on this Jablonski diagram? Aditya, what do you think?
What are the chances or what are the arrows?
What What arrows correspond to this solid line spectrum right here?
Would it be
So,
the solid lines going downwards that are next to the Roman numeral 3?
yes, exactly right. It could be these guys or it could be these guys. There's nothing in the information that we have here to distinguish between those necessarily. So, but the fact that they are solid and they're downward means that they correspond to emissions. This is the emission scan, right? So in this emission scan, what was the excitation wavelength? At what wavelength was energy put into the molecule such that we could monitor the emission between 350 and 500 nanometers? Can you guys read this?
There are like 400, 390 something.
Okay, so that would be about this wavelength here, right? The other option is 250, right? Either either 400 or 250 nanometers was the excitation to produce this emission. So let's say that it was 400 nanometers, right? Is it possible to put a 400 nanometer photon in and get a 375 nanometer photon out?
No.
Exactly. That would be, I mean, unless it's really hot. And in that case, there would be a stronger process to the right. There's not a weaker one. So we know that if we excite at 400, we're only going to get emission at wavelengths the red with a longer wavelength side of 400, right? Therefore, for this excitation, we're talking about 250 nanometer, I'm sorry, for these emissions, we're talking about 250 nanometer excitation. Does that make sense?
I have a question, Dr. Taro.
Yeah.
You said that with the information that we currently have, there's no ability for us to discern which peak is either the fluorescence or phosphorescence.
Mm-hmm.
Could it be said that the fluorescence has more energy, therefore a lower wavelength? So it should be a lower wavelength peak than the phosphorescence?
Yeah, you could certainly say that. Yeah. I mean, if we kind of knew the energies on this diagram and whatnot, we could piece this together. But just this is a generic Jablonski diagram. This is a real spectrum. So
Okay.
I shouldn't actually be asking these questions in this case because there's not a one-to-one correspondence here. Does that make sense?
Yeah, if the Jablonski was corresponding to that, then it would make sense. But, okay.
Right. Yeah. So don't tell anyone that I did this, okay? I'm gonna get in trouble.
Oh, they don't oh, okay. That's why I was confused. Okay.
Yeah. Especially you, Kai. I don't want you ratting me out. Oh, Kai's gone. I wonder if he went to drink. Oh no, he's still here. Good. So you're gonna rat me out, Kai?
Only to Calvin, so it's okay.
Oh, Calvin's gonna rat me out. Okay, all right. Well, he's gonna probably bribe me first, so we'll just have to see.
Smart man.
I'm in trouble, man. I'm in trouble. Okay, so now I searched for a while today and I couldn't find really good instructive literature on single molecule fluorescence, but I did find a good review article, and I've got a couple. Now, I have the article in the. I'll link it in Canvas and whatnot, but I don't necessarily want you to read the whole thing because it's a lot. But let's try and appreciate this this figure here, right? So now there's just so much to unpack in this. It's an amazing figure, right? And it's of a molecular motor that is, in some critter, right? It's probably in some membrane, right? And this molecular motor, what they did was they coupled a fluorescent molecule to the part of it that rotates, right? And one thing that we haven't discussed about fluorophores yet is the fact that there's only one polarization of light generally that interacts with a fluorophore, right? So let me see if I can get my stupid thing going here. So I'll try to get this guy focused down. So for example, there's a class of dyes called still beans. I think this is still bean, trans still bean, right? And when it absorbs light, it becomes this strange cationic form here, which is oh wait, no, sorry. Double, single, double. Right. So when light interacts with a still beam, I'm sorry, this is a single bond here. When a certain wavelength of light is absorbed by the still beam molecule, it gets this humongous dipole moment. And it's really common actually for fluorophores to do this type of thing. There's there's a certain amount of work that the photon does on the molecule, and it's always separating charge. In the case of the still beam, it separates it right along the molecular axis. Right? So we get a dipole like this, right? That's the physics dipole with the positive at the end of the arrow, right? And I don't know what the dipole moment of the ground state is. It's probably, who knows? Who knows what it is? But, it's probably small. Let's say it's small and pointing that way. And then when we're done, it's large and pointing to the left. Well, one thing that, and this is actually the psi star state, and this is psi, right? So you can see how the transition dipole moment operator here would have to do with movement of charge along this sort of x-axis. We've got x, y, and z here. This would be h nu moves charge along the x-axis, right? And so you can imagine then that the polarization of the photon the polarization of the photon that excites this transition matters, right? So let's just imagine then that, let's just take this molecule and let's say that, let's give it a sort of a vector shape here. That looks like this. Okay. And so this is the pyridine end, and this is the aniline end. Right? This is pyridine, and this is an aniline, and then there's this ethylene coupling here, right? And let's just say that we're looking at this molecule, and it's like this, and the light is coming in orthogonal to the page, right? Such that this light then can have any number of types of polarization. But let's think for the moment about linear polarization states of the photon. And so the polarization states of the photon can be like this. It can be like this. They can be like this. And they can be like this, right? So I'm going to have to color this guy in. It's hard to distinguish it there, right? And so this is going to be sort of in the YZ plane of the molecule, right? This is going to be oops, this is going to be Y, that's going to be Z, and then X will be sticking out from the page there, right? And this is the photon polarization. Right? And so if you were to guess which of these polarizations can separate the charge, let's label them 1, 2, 3, and 4. I've labeled 4 different polarization states. One is polarized along the y-axis. 2 is oh shoot, I screwed this thing completely up in terms of my my labeling. This is going to have to be the x-axis here, and then the y-axis here, and then the z-axis will be right, and then the z-axis will be pointing out of the plane. So this is z. So 1 is polarized along the x-axis. 2 is 45 degrees between x and y. 3 is along the y-axis. Right? And so basically what we're saying here is that number 1 has the polarization axis like that. And number 3 is the polarization axis is like that.
Dr. Terrell, can you please move the piece of paper?
Yes, sorry.
Thank you.
Of course. Yeah, a little over focused there. So this is the molecule, right? This is the stilbizolium. And this is maybe, this is the pyridine end, or this is the aniline end, that's the pyridine end, aniline end, pyridine end, And it doesn't really matter which end is which, it's just whether or not the polarization is lying along the molecular axis or it's orthogonal to the molecular axis, right? Because light has a direction, right? And it can only, if we oriented the molecule such that the molecule were sticking in and out of the page, then light actually would never interact with that molecule. To induce fluorescence. Right? But of these light polarization, we've got the polarization vector there and the polarization vector there of the light, right? Which of these two polarization axes will interact with the molecule such that it creates this charge separation state here? And I will who can answer that question? I mean, and just throw out an answer, right? So whether it's two has an equal likelihood of interacting or not. So it's really 1 or 3 that has the highest likelihood of interaction to separate charge along this axis. And it's if the E field of the light is orthogonal to that axis or if it's along that axis.
Is it number 3?
All right. Why would you say it's number 3?
Because the light is interacting with that double bond in the middle, so maybe.
Oh, I see. So that's basically just an artifact of how I wrote it. I could have wrote it like this with the light.
Oh, gotcha. Okay.
Yeah. So the light will have equal access to the double bond.
Okay.
But so do you want to change your answer or no? Oh, this is wait. Oh. Okay, forget it. Now you need 3 choices for it to be that funny conundrum. Okay. So do you want to change your answer or no?
I'm not quite sure yet.
Not sure. Okay. So the ground state is like this. The excited state is like that, right? Now, the way to get from this to this is by absorption of a photon. The photon has to do work on the electrons in this molecule. And the work has to have the net effect of moving an electron from this end to this end, right? You have to take a molecule or an electron at this end and move it to this end. Or you take an electron from this end and move it to this end. So that this is left positive and that one's left negative. Right? So now, if the electric field is in this direction versus this direction, which of these 2 electric fields can do the work to move the electron from this end to this end? The electric field in this direction or the electric field in this direction?
The horizontal one?
Okay, what do you say?
Because if the electric field is going from left to right, then I assume that the electron can move along that field.
Yes, exactly right. Exactly right. Does that make sense to everybody? Good. I like it, Mike. Makes sense, Kai. Good. Okay. So this is called polarization anisotropy. Oops. Oh, so weird. If I'm looking at the screen and writing, there's a little delay. It freaks me out. So I have to look at the page, not at the screen. So the polarization anisotropy of the still beam is very clear, you know. And so there's really, you know, you can rotate this stupid still beam in 3 dimensions, right? There's really only one orientation in which it has a significant chance of interacting with the electric field, right? So that's one of the things that will lower the quantum efficiency of the dye, right? Is the orientation. Okay. So so what if instead of a photon coming out of the page like this, right? Let's just say that this is this circle that I'm drawing here indicates that the photon direction is into and out of the page, right? Does that make sense? Good. So what if a photon, instead of going into the page with its E field oscillating in the page, like this, what if it's coming and it's coming along this way and the E field is oscillating up and down like that? Can this photon interact with this molecule to create this excited state? Who should I talk to about this? How about you, Leslie? Do you want to talk about this?
I actually don't. I honestly don't know.
Okay. So you get the part about the photon, in this case, going into the page, and in this case, going into the page?
No.
Okay. So you know how when a photon, like if a photon is moving from left to right here, the electric field intensity is going up and down, right? And it's going up and down normal to the direction of the photon. So this is the photon direction. And the electric field is going up and then down, and then it'll go up and down. But it'll always go up and down in it at right angles, normal to the direction of propagation. Does that make sense?
A little.
A little? Okay. So it's kind of like a swimmer swimming along and doing, you know, let's say his arms are, he's doing freestyle, right? Well, if a swimmer is going along in this direction, then his arms are going to be going around like this, right? And you could say that his arm, the projection of his arms were going up and down, sort of normal to his direction of motion. Does that make sense?
Yeah.
Okay. So for a photon, the the electric field goes up and down, say in the page, and that scoots the photon along in this direction. Yes? Doesn't make sense? Makes sense or doesn't make sense?
Are you asking me or the class?
Does this make sense to anybody else in class, or am I just completely like everybody just like, the hell with this guy, he doesn't make sense. I'm gonna quit and I'm gonna move to Tahiti and I'm gonna become a surfer dude. I'm gonna learn to do this. Which I think means like something in Hawaiian.
Tahiti sounds good.
You could also stay in
Tahiti-
California and do that.
Okay, yeah, you could do it in California too. I mean, but you know, you got to get far away from me. Kai. So Richard, does
Yeah.
this make sense? That as the photon goes left to right, that the electric field goes up and down.
That makes sense, but I keep thinking about like electromagnetism. Isn't there something in like the field of electricity is orthogonal to the magnetism or magnetic field, or is it?
Yeah, sure. There's a magnetic field. The magnetic field in this case would be coming out of the plane, into the plane, and out of the plane, into the plane.
Right.
But let's focus right now on the electrical part, right? Because the electrical part is actually going to do the majority of the work on the electrons. The magnetic part is, it's there and it's more important at higher intensity. But at these lower intensities, let's think only about the electric. And so basically what I've said, I basically defined the three possibilities for polarization of this photon. Either it's going to be going up and down, left and right, up and down into the plane, left and right into the plane, or up and down in the plane. It's kind of like X, Y, and Z, right? Actually, there's more choices, but I think there's, you know, for this direction, you could be going, you can have the electric part coming in and out too. But actually, that's not going to change the question that I have on the table. The question is, can this photon here, this photon, whose name is George, can he be eaten by this molecule here, whose name is Pauline? And that's not to imply it's just a random name. I did not mean to imply that you eat photons.
No, I think you said that I was getting eaten.
Oh, no. You're eating photon. Oh, I gave it away. Pauline eats photons. Pauline is a photon eater. So here's Pauline, here's the photon. And there's just three polarizations, A, B, and C, right? A and B, they both go in and out of the plane. And C is in the plane of the paper, right? And we already determined that in order to drive this transition from this ground state to this excited state, we would need to have which of these three polarizations, A, B, or C?
We said C earlier, right?
That was a good guess. I don't know. Adam. Oh, somebody said C. Ivy said C. C is incorrect. Richard said C. C is incorrect. In order to separate charge along this axis here, you got to move an electron from here to here. So that we leave this state plus minus. Right? And we need the electric field to be along this axis or this axis. And the person who answered that is silent. Calvin says B. I think that is by process of elimination. Absolutely correct. Adam now says B. Does anybody want to go along with Calvin and Adam? Take a chance. Carla, do you want to take a chance? I think so. What do you think, Leslie? We're getting B's all over the place. Ivy, Carla, Kai. Richard says B, as in B, the bumblebee. Kenya says B. Pauline has not weighed in. So anyhow, so yeah, so B, we need to, the electric field, let's say if the electric field is pointing this way, and this side is positive, right? Then it's going to take this electron, it's going to move it to its positive end, right? So that's how it works, right? The electric field works on the electron, and it moves it from one end of the molecule to the other. It separates charge, and in so doing, it sacrifices its own stupid life, right? A photon gave its life for you, Pauline. You understand the gravity of this situation? I can shut up. Okay, so so here's the ground state, here's the excited state. That's because the photon polarized along this axis here did work on that electron, right? So I'm asking you now whether a photon coming in this direction with this oscillation can do the same work that photon B did. The answer is yes or no, making your chances today about 1 in 7 of getting the answer right. And so everybody's going to vote now on chat. Yes or no, that photon C, George can be eaten by Pauline. Yes or no, vote. Oh, no. Okay. All right. So that's right. It's no. So why didn't you guys just say that? Gosh, you're so quiet. You're leaving me hanging out to dry here. Okay.
Vote in chat.
Oh my gosh, I don't know. You got to speak up. So, hold on. That's not how I do that. So now I got to go back to this guy, right? So, now here is such a molecule, right? On this, and this molecule is on a rotating part of this protein, such that its transition dipole moment, ta-da, can rotate around this axis. Da-da-da-da-da-da-da. Even better, this is a stupid membrane-bound protein, which you can lay flat on a microscope slide. Right? So then you can irradiate this guy with light coming down in this direction. Does that make sense? Yes. And then this transition dipole moment can orient or be orthogonal to the plane of polarization of the light coming down depending on the rotational state of its anchor here in the protein. Does that make sense? Yes or no? Somebody say something like,
Yeah, can you explain that again, please?
sure, absolutely. This is a protein, this green and blue blobby thing. And this protein is normally bound in a membrane, right? So a membrane would be out here. Right? So this protein can't tumble in space. It's fixed in a 2D plane. That make sense? Yes? Okay. So this red part here can rotate. It always rotates along the same axis that sticks up out of the plane of the protein. Does that make sense? Yeah, good. And light then can be focused, or light can be incident on this protein dye assembly, such that the light comes down, insert a stupid shape like this, come on. Light comes down like this, right? And let's say that light has the plane of has its polarization in the plane of the paper, here, in the plane of the screen, such that when this light bulb is oriented along the screen, it will turn on, and when it's oriented out of the screen, it will turn off. Does that make sense?
Yeah, it does.
Yes.
Oh, I love it. So now the fact that this is in publication means that it worked, and they're able to observe, they're able to take pictures of this little bright spot on their microscope slide. They're able to watch it go dark, bright, dark, bright, 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 dark, 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 bright. Isn't that cool? That means that this thing rotates about, 20 times a second. Or who knows, maybe 5 times a second, something like that. Or maybe once a second, actually. Looking at the data here, maybe.
I think it rotates really fast because it's the one that produces ATP.
Oh God. I think it uses ATP, doesn't it? Or does it
So
produce
it makes it. So the reason
yeah.
why it's rotating is because it's taking the
The
phosphate.
ATP, the
It's
phosphate, then binding it.
Shut up. Psi3 F1 ATPase molecules, right? So are you saying that when it rotates, it creates ATP, or that when it rotates, it uses ATP?
It rotates like it makes ATP.
It makes it, yes.
It makes it? And how did you guys know that?
We learned it in biochem.
Oh my God. An F1 ATPase motor.
You're cheating.
This is a Psi3 F1 ATPase. Right? Isn't this cool? Anyway, so what they were able to do was, and this is membrane bound, right? It's in a mitochondrion, right? It's in a mitochondrion. That's cool. See, I'm learning biochemistry. So let's just see. So here is the intensity versus time as this thing goes up and down and up and down and up and down. They have a fit. Looks like the red is a fit and the black is the actual data. Right? But it's clearly, oh God, who knows? It's clearly rotating with this period. I mean, there's no question about that. And then I think it's like when it goes around, like, I don't know, like from a peak to this peak here, that's one rotation. Right? And so this is like 1, 2. I don't really get this stupid purple line. I don't exactly understand how they got it. But basically, the thing must be rotating, right? And if it could be 3 total rotations in 10 seconds, okay, cool. And then the orientation, who knows? It's kind of going up and down and up and down, but it seems like it's going smoothly. It doesn't seem to be going in little steps to me. So I don't understand all of this stuff. But in any case, you can do all kinds of things with these data, but it's only because you're looking at a single fluorophore that you can get this type of data. Does that make sense? I suspect. Oh, polarized glasses, yeah. Oh, okay, yeah. Oh, so yeah, the photons are cool, right? And it wasn't really appreciated, well, anyway, I didn't really appreciate it until I saw a laser beam, right? Yeah, I thought electromagnetic waves always just were spherical wavefronts. But no, they actually travel in a direction, a single direction. And so with a laser, it's very simple to control the direction. Just point the damn laser, and it goes from the laser to whatever the laser is pointing on. And I say that not like, oh, what a stupid question, because it was really a revelation to me, that's like there's a source and there's a destination, there's a time delay between those, right? And the photons that come out of the source move along a straight line from the source to the destination. And if you put a polarizer in that beam, then all of the photons that are moving in that direction will have the same electric field vector. The electric field vector will all be aligned, right? For all those photons. And all those photons travel at the speed of light because they have no mass. Anyway, it just gets interesting.
I thought it was because they were traveling light.
I love it. Nerd humor. Nerd humor. That makes sense. LOL. I like it. Polarized glasses. Okay, cool. So, so this is one way to analyze these molecules on a single molecule level. I mean, this is just, this takes a lot of work to get everything right just to see a single molecule. I'm not saying that this is going to take over the, the sort of the biophysical world, but in certain areas, it could, like there's protein folding. So here's a this is a ribozyme from Tetrahymena, whatever Tetrahymena is. That's some creature, probably some single cell creature, right? And here's a ribozyme. They've modified that ribozyme such that it has the Psi5 and the Psi3 fluorophores that are either close or far apart, right? And the two states, the two folding states or the two docking states of this protein move these Psi3 molecules into proximity, or Psi3, Psi5, right? Or it separates them, right? And they've arranged it such that in, I believe it's the undocked state here, there's the transition dipole moments of psi 3 and psi 5 are orthogonal, such that you can excite one but not the other with a given type of photon, or a given direction of photons. You know, basically, you just point the laser in a certain way, and you can excite the psi 3 but not the psi 5, right? Or the psi 5 but not the psi 3. Right? I'm not really sure. Right? But then when it docks, whatever that docking is, I couldn't actually figure that out. Then these guys are in proximity, and then this one goes down and the other one goes up, right? So in this beautifully noisy signal, you can ratio this green one to the red one, right? Or I don't know. It's actually a different, it's A over D plus A, right? So I think that must be red over red plus green, right? And so it's either one or something less than one, right? And so they can observe the single protein molecule folding and unfolding on this, multi-second time scale. This ribozyme doing its ribozyme thing. Does that make sense? Okay, so let's read the caption here. Single molecule ribozyme folding. A model of the reversible docking reaction on the P1 recognition helix on the rest of the tetrahedron ribozyme. The P1 recognition helix is formed by base pairing between the 3' end of the ribozyme, gray, and the substrate, S, blue. Right? So this substrate here, this blue thing, docks down here, right? With the azidophenyl acyl group at the 5' end of the ribosome. P1 duplex cross-linking occurs at different positions in the undocked and docked states, right? So basically, the duplex cross-linking occurs at different positions. Whatever. Distance changes during the reversible docking between CY3, the fluorescence donor, and on S and CY5, the fluorescence acceptor, it's red on the tether. So the FRET signals fluorescence resonance energy transfer is what FRET stands for. Are IA over IO plus IA, right? And the donor green, which is green, and the acceptor, which is purple, or red, whatever they call it, red, as a function of time, the calculated FRET trajectory, the blue top. This is the calculated FRET trajectory. So this is the fluorescence, right? And basically, when it docks, then you can transfer energy between these two dyes, right? And then what happens is you see less fluorescence from Mr. Mean Greeny side 3 here, and more fluorescence from, oops, you see less from the red and more from the green, right? I think the colors are opposite of the actual colors of the fluorescence. That's unfortunate, but Donor green and acceptor fluorescence time traces. So this is the donor and that's the acceptor. So when this folds, you excite this molecule, and it can transfer its fluorescence density to this one. And you see this increase in the acceptor energy. Right? Does that make sense? So this is a donor-acceptor pair. And FRET, fluorescence resonance energy transfer, is the same phenomenon that underpins quenching in aggregate pairs. Right? You know how when you take, back to the SMILES article, when you take fluorophores and you pack them together, the fluorescence goes way down. Right? That's because in those solids, you put everybody into the FRET radius with other neighbors, and the resonance energy transfer can hop through the crystal until it quenches. It essentially dramatically increases the lifetime of the excitation, which is now called an exciton. And that exciton hops around until it dies, and you don't get any light out. Right? In this case, this excitation just can make one transfer from the green one to the red one. Then the red one can't transfer it back, so it emits a fluorescent photon. Isn't that cool? So this is a case where they took this phenomenon of similar fluorophores, like Psi3 and Psi5, that can exchange their excitation energy through space. And they used it to monitor the folding state of this ribozyme. Does that make sense? I need to hear some amens here, man, because I'm freaking out.
Amen.
Amen.
Amen. I need to hear some amens. Thank you. All right. Well, that's all I got then. You guys, you're just sucking the life out of me today. I'm going to go have a gin and tonic because it's Thursday, which is my Friday.
Me too.
Amen. 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 Woo! Hey, I think everybody's sacrilegious, even the people praying in the churches. So if it's going to benefit them, it better benefit me. Bye, everybody.
Bye.
Good night, Dr. Taro.
Bye. Good night.
Have a good weekend.
Good time with your gin and tonic.
Enjoy your
Yes.
gin tonic.
Thank you. I will enjoy it. Thank you.